These notes on momentum and impulse will be 15 minutes or less. At 15 minutes, I'll stop regardless of where we're at, and we will finish up in class. So momentum and impulse is our next unit, and once we get through that, we'll be talking about the conservation of momentum. But in the beginning, we're just going to concentrate on momentum and impulse. So we're going to relate this unit to inertia to start off with. We know that from Newton's first law, right, an object at rest stays at rest, an object in motion stays in motion if the net force acting on it is zero. And we related that ability to stay in motion or to stay at rest, we call that inertia. Sometimes Newton's first law is also called the law of inertia, and we know that the more massive an object is, the more inertia it has. So, right, we know it's an object's resistance to change in motion, and if this goes too fast, obviously pause the video so you can fill in your notes. The more massive an object has, the more inertia it is, so it's harder to change that motion. Now remember, change that motion doesn't just mean get faster or get slower, it means accelerate, and acceleration can be it's slowing down, it's speeding up, or it's turning. Turning is also changing its motion because it's changing its direction. So we know that it would be easier to change the motion of a person, right, a 60 kilogram person on a skateboard compared to an elephant on a skateboard, right? If that person was coming at you and the elephant was coming at you, it seems pretty easy to stop the person compared to an elephant, or vice versa, right? It would be easy if you got behind this guy and you pushed the person on the skateboard, you could get him moving pretty easy, but the elephant would be much harder because he has so much more inertia because he has more mass. We've also talked way back in August, right? We talked about velocity and acceleration, and we know that velocity, right, is just it's changing position versus time, or for us, how many meters an object travels per second. Right? We know that you need a large change, right, to get to a high velocity, or to stop from a high velocity. A large positive change in velocity would get you to a high velocity, or if something was moving at a high velocity, right, a large negative change would slow that object down. Well, momentum, it's really just putting the two together. It's putting together the mass or the inertia of something and the velocity. So momentum, right, a measure of how difficult it is to stop a moving object. Or it could be the opposite, a measure of how difficult it is to start a moving object. But essentially, the reason why you focus on the moving object part is because momentum is not just inertia, it's also that velocity and how that velocity plays an impact on it. So if an object isn't moving, it still has inertia, but it has no momentum, right? Hence why we're going to focus on the moving part of it. So both inertia and velocity determine the momentum of an object. So it's very easy. Momentum is just the mass of the object. Remember, it needs to be in kilograms, multiplied by the velocity, and of course in meters per second. So kind of weird, the symbol is a P, a lowercase p, right? A capital P would be pressure, so lowercase p, and then MV, the units for it, you know how like we have newtons, which is kilograms times meters per second squared. Well, for momentum, there isn't any shorter version. You have to write out just the pieces that make it up, which are your kilograms, right, your mass, times your velocity, meters per second. So every time you write the units, you have to write kilograms and then times meters per second. Okay, so we have this elephant and the man. Right now, if the elephant and the man were both coming at you on a skateboard and you were stuck, you were going to have to stand in front of one of them and figure out, okay, well, who am I going to stop, right? Who are you going to stand in front of? Your first instinct says, well, I'm going to stand in front of the man. Absolutely stand in front of the man. The elephant is way too big. I can't stop that guy. Let's change it up a little bit. Let's say the man is just, he's just moving at Mach 1, right? He's moving at the speed of sound, And that elephant, he's crawling. He is barely moving at 0.01 meters per second, right? 0.01 meters per second. What is that? That's 1 centimeter a second. I mean, you're talking an ant crawls faster than this elephant is moving. So who do you want to get in front of and stop? Well, you have a better chance with the elephant because the man has so much more momentum, right? The man has 340 times 60, where that elephant only had 0.01 times the 1,000. So the elephant had what, 10 kilograms per, or kilograms times meters per second, and that guy, that kid on the skateboard, will, you know, you'd be toast. Okay, well, momentum by itself really isn't that big of a deal. We're going to be more concerned about changing the momentum of an object, and that's where, right, that's what we want to do, is we want to change the motion of an object. We don't care about just its momentum, but how that momentum changes. So, right, the momentum can change by changing the mass of the object or the velocity. Well, changing the mass is really actually pretty rare. And, you know, if you're thinking about, you know, you're driving down the road, how are you going to change the momentum of your object? Well, you're not going to start unbolting seats and throwing them out the window, right? If you're that kid on that skateboard and you want to change your momentum, what are you going to do? You know, hack off an arm, throw it out? No. Your velocity is going to change, but it can change by the mass. And actually, NASCAR makes cars that, you know, when those cars hit the wall, yeah, they're moving really fast and all the pieces fly off, but those pieces fly off on purpose because every time a panel of that car falls off, that car loses mass, which means it has less momentum. That means it's easier to stop that car because it has less momentum. But we're not going to mess with changing mass very often. We're mostly going to focus on a change in velocity. So if we're going to change momentum, technically the equation says you would say change in mv, right? But we're going to change the v. Actually, on the formula sheet, you're only going to see two formulas for this whole unit on the formula sheet, and one of them is momentum, where it just says P equals mv. It doesn't have the delta P and the delta V. Okay, impulse. Well, how are we going to change the momentum? I said that we wanted to focus on the change in momentum more than the momentum. So how are we going to change it? Well, you change it by applying an impulse. Impulse and momentum are very similarly related, as in work and energy. If an object has 0 joules of energy, how are you going to give it energy? You're going to do work. Or if an object has energy, what can that object do, or how does it end up, you know, stopping? Well, friction does work, right? Friction takes that energy away from it. Well, this is going to be kind of the same thing with impulse. If you have an object that has no momentum, how is it going to gain momentum? Not only is it just the force, but it's the length of time that that force applied causes the change in momentum. Or the opposite, right? How are you going to change the momentum of an object that's moving really fast? How are you going to get it down to 0? Same idea. You're going to apply a force over time and bring it down to 0. So impulse is a capital J. You won't see that on the formula sheet at all. It won't say capital J. It'll actually say delta P equals Ft, because how you change the momentum of an object is you apply an impulse. So we know force is in newtons, right? Time, of course, is in seconds. So our impulse is just going to be just like momentum is kilograms times meters per second. Impulse is going to be newtons times seconds. And actually, if you separate out the newtons, right, newtons is kilograms times meters per second squared times the t of seconds, you end up with the same units for momentum as kilograms times meters per second. So really, if they ask for the momentum or the impulse of an object, you can list the units as kilograms times meters per second or newtons times seconds. Okay, so an object can have the same change in momentum by having either right? A large force but a small time, or a small force but a large time. So those are two distinctly different things. I mean, when you start relating it to other things, and we'll get into some examples and you'll see how that makes a big deal. Okay, rifle versus a pistol, right? You pull the trigger, the hammer comes down, it lights that gunpowder on fire, it causes the gas to expand. Well, if the barrel of your pistol is, let's say, 4 inches long, 3 inches long, well, that means the force was only applied over the time that it took for that bullet to move 3 inches. So not much time. So that bullet comes out, it's not moving necessarily quite as fast as it could be. Well, in a rifle, now all of a sudden your barrel maybe is, 70, 80 centimeters long. And now that force is applied for a much longer period of time because the barrel's longer. And so because the force is applied for more time, the bullet's going to come out moving faster. Airbags in a dashboard, right? They used to make dashboards out of metal, and people didn't wear seatbelts. So you get a car accident and your head hits that metal dashboard, what are you going to get? You're going to get a very large force because your momentum is going to change in no time at all. Right? And then over time they made foam dashboards. Well, now we have airbags. What does that do? That airbag extends the time. Now instead of a fraction of a second, maybe it takes a couple fractions of a second. But every single fraction of a second that you add on to the time to stop decreases the force. You get double the time, you get half the force. That's huge. From 2 milliseconds to 4 milliseconds, and you get half the force that's acting on your body, your head, your chest, so on to stop. It makes a huge difference. So either way, your momentum will change down to 0, but how do you want it to change to 0? Well, I'll take a large time and a small force compared to a small time and a large force. If you're driving your car and you want to stop, you got two ways that you can do it. You can run into the guy in front of you, right? You'll stop really, really fast, but there is going to be a huge force on you and the car. Or you hit the brakes and you come to stop nice and slow, and that way by extending the time it takes to stop, then there's less force. Right, I don't know if we're going to get to this, but right, making an egg when you drop it off the side of the building, right? You drop it off the bleachers, what do you want to happen? Well, when it hits the ground, its momentum is going to change to 0. There's nothing you can do about it. It's going to go to 0. It's just, how does it happen? If you can extend the time it takes for that from the point of impact to the time it stops, which is just fractions of seconds, if you can make it take longer, you get less force and your egg doesn't break, right? So you drop it, it's in free fall, it's accelerating at 10 meters per second the whole entire time until it makes contact with the ground. It's no longer in free fall, and now that force of the ground is causing an impulse on your egg. Let's see, I wanted to do one other thing about this. The only other thing is, like, think about if I was to, let's say, throw you a baseball. I'd throw you the baseball. If I wound up, I threw it as hard as I could throw it, right? When you catch it, just what would your hand do? You would kind of catch it and your hand would move backwards a little bit. And the reason your hand moves backwards a little bit is to extend the time it takes to stop that object from moving. So the impulse is the same, but the way that impulse applied is vastly different. Think about, if I threw a baseball and told you, what, I want you to set your hand up against the whiteboard. I want you to set it there all the way touching the whiteboard. I'm going to throw the ball as hard as I can at your hand and you catch it. You'd break your hand, right? Because that ball would stop instantly because there'd be a large force. The impulse would be constant regardless of how you catch it. The change in momentum would be constant regardless of how you catch it. But the way that the impulse is applied makes a big difference to your hand. So this next page is about the impulse momentum theorem. This is where we will pick up in class. We'll do this in a couple examples, and then you'll have some time to work on your homework.